I'm a researcher at the Institute of Computer Science at Forth, and I'm going to present to you today a webinar about the OLQ and its use in order to specify the semantics of BPaaS. So you can see here how I look like. So, and just some details about the webinar before I start. So first of all, you should have all your microphones muted in order not to have any voice interference. And when I stop my presentation and finish it, then you can ask questions into the chat window, as you can see in the slide here. And I will be able to answer your questions. The presentation will take around 30 minutes of pure time, and then there will be 5 to 10 minutes for questions. So this is the agenda of the webinar. First I will introduce what is OLQ, then I will indicate what are the main application areas of this language, then I will follow the analysis of OLQ and especially its two main extensions, and finally I will present a summary of the presentation and I will answer your questions. So what is OLQ? OLQ is a semantic language for non-functional service description, which is based on the W3C standard. This language has been carefully designed into several facets, and each facet maps to a particular measurement aspect being covered, and it also includes a set of SW rules, semantic rules, which enable to validate the OLQ models, as well as to produce added value knowledge, which in the current situation maps mainly for knowledge about facts, matchmaking facts between QoS terms. This language has been originally developed for service-oriented computing, but now has been extended in order to cover cloud computing. And based on its expressiveness and its well coverage of the respective domain, it has been considered as the most prominent language in ACM computing service paper on service quality description. And in the end of my slides, I also provide you with a list of the references that are mentioned inside this presentation. So in the next slide, you can see the current application areas of OLQ. So OLQ has been used for non-functional service description, service matchmaking, service selection, service negotiation, SLA management, and KPI evaluation. I will slightly focus on the underlined areas, and of course the last two areas will actually be covered by analyzing the two extensions of OLQ concerning the description of SLA and the KPI evaluation. So for non-functional service matchmaking, I have proposed two types of approaches, and the first one is relies on ontology-based assumption. So what is actually done is that ontology reasoning techniques are used in order to infer the assumption relationship between the current QoS offer and the respective QoS offers that have been of QoS demand and the respective QoS offers that have been stored in the respective knowledge base. And this kind of assumption will actually work only if both types of specifications, that is QoS offers and request, are actually specified at the class and not instance level. The second approach is called mixed one. So what it tries to do is that first of all it tries to align the QoS-based specifications based on the quality terms. Then it transforms the specifications to a constraint problem or to a set of constraint problems, and then depending on the linearity of the constraints that are involved in this problem, a particular constraint problem solver is being used. more details about both the non-functional service matchmaking and selection for, especially in the context for BPaaS allocation, will be provided in a forthcoming webinar on April. Now I would like to focus a bit more on one of the steps involved in the second approach, or the next one, which is called ontology alignment. So what it tries to do is to deal with the following issue. If we observe, let's say, the current situation in the service and cloud world, we can actually see that in the respective specifications, such as SLAs, there is a structural and semantic heterogeneity of the, with respect to the QoS terms that are being exploited and used in these specifications. This means that similar or equivalent QoS terms are defined in a different way, or that different QoS terms are specified with the same name. And this kind of heterogeneity actually leads to low precision and call in the service discovery process. So one way to address this is to align the QoS specifications based on their QoS terms, and especially on the QoS metrics, which are the type of QoS terms that are being used in the constraints of the QoS specifications, where constraints actually map to the respective requirements that are demanded or the capabilities that are being offered by the corresponding services. Now, the approach for the ontology alignment is that, first of all, we maintain a set of primary QoS terms, and then for each QoS specification that we process, we compare its terms with the primary QoS terms. So if we find a new term which is not matched with the primary QoS term set, then we enter this term into this set. If the term is matched with a respective primary QoS term, then we align the QoS specification being processed. This means that we replace the matched term with the primary QoS term, and in all the constraints that the matched term is being involved, we actually modify it and make a respective transformation in order to cater for unit differences between the matched term and the primary QoS term. The matching of QoS metrics relies on three main semantic rules, which cater for the comparison between different types of metrics. So I would like to mention here that raw metrics are metrics which are, derived immediately from the service instrumentation system via measurement directives or even from sensors, while composite metrics are aggregations of other metrics. So they are produced by respective formula involving these component metrics. So in this sense, there are three rules which try to compare raw to raw metrics, raw to composite metrics, and composite to composite metrics. And now I'm going to give you a very small example of how alignment is being performed. So suppose that there are two QoS offers which refer to equivalent availability metrics, and its metric is specified by the respective formulas that you can see in the slide. Now, what is firstly done is that we try to match the formulas of the two metrics. So if we check the respective component metrics involved in these formulas, we will be able to see that uptime and downtime metrics, which are involved in these formulas, are raw metrics, and they are indeed equivalent because they map to the same units, value types, and measurement directives. So in this way, what to do next is that we transform both of the formulas into a new form which contains only the unique and matched metrics. After you do that, then you have a uniform way of specifying both of the formulas, and what we try to do then is to check whether the difference is equal to 0. And we actually use for this purpose symbolic calculation techniques. So in the end, by examining the example, you can see that the difference is equals to 0, And as the two metrics map to the same unit and value type, which is ratio for unit and the set of real numbers from 0 to 1, then we actually infer the matching of the two availability metrics. Now I'm slightly indicate how OLQ has been applied to service negotiation, and then I will move on to the analysis of OLQ. So concerning the negotiation support, OLQ has been extended slightly to indicate, first of all, whether the QS terms involved in the QS specification are negotiable, and what are the admissible value types for these QS terms that can be exploited during the negotiation in order to find, let's say, a common value and to be imprinted in the resulting SLA. In order to support the negotiation, in this case, based on the OLQ extension, a respective matchmaking algorithm based on OLQ has been updated and has been actually used in order to support the negotiation in terms of assisting the negotiation participants of checking whether an offer or a counter offer matches their own requirements and expectations. Apart from this extension, we also realize another approach which complements the previous one and tries to find common negotiation protocols between all the participants in a negotiation in order to initiate this negotiation with one of these protocols. The main issue here is that we don't do a simple matching, a corresponding matching based on the names of the protocols or the actual, let's say, semantic description, but based on a fine-grained description of protocols, mapping to the actual split into respective protocol actions. And then we check whether each participant is able, based on its respective role in negotiation, is able to actually support the respective action either by himself or by an agent that is able to represent him, or by doing a delegation on other let's say indirect participants which belong to his network. Now, let's move on to analyzing OLQ. So OLQ has been recently refactored based also on the findings of the survey paper in order to reduce its size, to become more focused, and also being enriched with respect to the validation and generation of the added value knowledge. In addition, recently a particular Java API has been produced, which can be used in order to programmatically create, parse, and write OLQ models. And this code can be used in order to support the generation of matchmakers or service selection algorithms, but can also be used in order to create customized editors for OLQ. For the time being, there is no customized editor for OLQ, but there's one planned, and in this sense, whenever you want to, if you want to, let's say, edit OLQ, then you will have to use well-known external ontology editors, like, for example, Protege. And now I'm going to introduce to you the 6 main facets of OLQ, which cover different measurability aspects. Here is a nice say, figure of OLQ. I will try to make it bigger for you to be able to show it. So, as you can see here, there is first of all the generic facet, having concepts colored with gray, in which it covers, let's say, the description of top-level concepts, which are more detailed later on in other facets, and also covers the specification of generic properties. For example, the name and description as property can be attached to any kind of concept which is used in OLQ. Now, the next facet is called the attribute facet, and includes, let's say, the description of different types of attributes. As you can see here, the concepts of this facet are colored with red. So we can have measurable attributes which are measured by metrics. We have unmeasurable attributes which are, let's say, static attributes for which we know already the values. And we have domain-dependent attributes, and we also have composite attributes, which let's say more abstract attributes which can be decomposed into more concrete attributes. Now the metric facet actually deals with specifying all the appropriate details for measuring a particular attribute, and the respective concepts are colored with blue. So as already indicated, we have a raw metric which can be measured via sensors or measurement directives, and you have a composite metric which can be measured by applying a particular formula over a list of metrics. In addition, a metric is mapped to a particular context which indicates how often the metric will be measured according to a schedule and according to which measurement window. In addition, a metric is mapped to a unit, and you can see here at the bottom of the figure the unit facet where the respective concepts are colored with the yellow color. As you can see here, there are three main types of units. We have a single unit, like for example a time-based unit as seconds or minutes and so on. We have a dimensionless unit which doesn't map to a particular dimension, and here you can have units like percentage or ratio. And we have a derived unit which could be something like operations, number of calls per second, which is usually expressed as a division between multiplications of units. And finally, in order to be able, let's say, to map metrics to particular value types which indicate the respective values that these metrics can take, we'll actually have generate a value type facet, which includes different types of concepts mapping to different value types. So we have a list of values as one kind of value type, and then you have scalar types, which can be, let's say, the whole space of integers, the whole range, space of floats, and so on. And we can also have ranges, so semi-closed or closed ranges for integers, floats, and doubles, and also unions of ranges. The last facet is a specification facet. So in this facet, there are two types of specifications that can be described. We have a QoS profile which indicates a non-functional service advertisement, and there's a QoS request which indicates a non-functional service request. So both types map to a particular specification which can be specified, let's say, as one constraint which can be simple or complex. And the complex constraints are logical combinations of other constraints, while a simple constraint is a constraint over a metric, which includes, in addition, a respective comparison operator or optimization operator if you want to maximize or minimize the metric. And in the case of comparison operator, also the threshold to be applied on this metric. A specification is mapped, of course, to one service, which can have components, and is also characterized by particular properties. And finally, for let's say for a particular QoS request, apart from the main specification mapping to the capabilities are required by this request, there's also a preference model which associates weights on respective QoS terms in order to assist in the matchmaking and selection process of services. Okay, here I'm providing you some examples of rules could be used for model validation and knowledge generation. So an example of a model validation rule would be that for simple constraints, the values of the thresholds should be within the value type of the respective metric on which the constraint is being applied. And for the knowledge generation, as I already indicated, there are rules which infer the matching between different types of QoS terms, like metrics, value types, units, and so on. Now moving on to the selection, the extensions on the respective OLQ. The first one is about the description of SLAs, and this extension has been say, generate, first of all, in order to cover, let's say, the requirements of the CloudSocket project, but also in order to fill a gap in the SLA world. So based on the analysis again of the survey paper in the reference 1. So based on this gap, actually, there is a problem with the completeness of the information that's being specified by the current set of SLA languages have been proposed, and this completeness affects the way that the service can be managed by respective service management frameworks. So what the extension tries to do is tries to cover this gap. It builds upon the specification that has been presented previously, and it can be used by different environments within the CloudSocket prototype. So in the case of BPaaS allocation environment, it can be used to specify SLA tablets within the BPaaS offerings, which are named as BPaaS bundles, and can also be exploited by the SLA engine in the BPaaS execution environment, which is able to monitor and manage the SLAs that are being signed between the BPaaS broker and customer. So what this SLA extension can do is the following. It is able to specify both SLAs and SLA tablets. It is also able to specify hierarchical SLAs, where on the top level you can have an SLA for the BPaaS, which involves the BPaaS broker and customer. And on the lower levels, it maps to SLAs between either the broker or the BPaaS customer and the respective cloud service providers. And as such actually relates to the actual services that are being used in order to support the execution of the respective BPaaS. In addition, this SLA extension can be used in order to model explicitly the service levels delivered by the respective BPaaS, which are expressed as logical combinations of SLOs. In addition, it's able to specify transitions between service levels, and this enables actual flexibility with respect to SLA management, because it caters for cases where SLAs can be modified on demand in order to move from one service level to another one, based on, let's say, change of particular situation. For instance, let's say the BPaaS customer now has more clients and has additional load, and it requires to move from the bronze service level to a gold service level in order to be able to accommodate for the increased load workload. For each SLO, which is specified as a symbol, let's say, constraint, we also attach qualifying conditions as well as penalties and rewards over the pricing of the respective BPaaS, as well as in the form of particular coupons that can be exploited by the customer. In addition, we are able to specify, of course, service price models, which are associated to the penalties and rewards, and also critical settlement situations along the respective actions that have to be performed for them. And this, of course, includes let's say, the conditions under which the SLA should be cancelled or renegotiated. Here is, let's say, a figure indicating the current status of the ontology and what it covers. I will not go too much into detail, but what I would like to indicate to you is, first of all, the SLA is a kind of specification which involves a set of role assignments, which are, let's say, assignments over the respective entities which are involved in the SLA. And each entity can play different roles, and the following roles have been actually imprinted into the OLQ specification. So we can have service providers, service requesters, brokers, and third parties like auditors. And these third-party entities can actually be used in order to monitor particular metrics are being involved from the SLOs, or evaluate the actual SLOs. In addition, I would like to indicate in this figure that the service level is a kind of complex constraint, as it's a logical combination of SLOs, while the SLO is a kind of a simple constraint. And finally, I would like to indicate that we cover the price model, which includes a min and max price, beyond which the price of the service cannot go. And this price model comprises price components which indicate how the price of the service is being computed according to different aspects. For example, if we consider a service, then the one price component could be used in order to measure, let's say, the price with respect to the computational resources, so how long this service has been used, while there will be another component which will attempt to calculate the cost about the uses of the network resources. As there's no time, I will move on. I will not provide you a more specific example, but you can check the respective reference of the SLA extension, and you can see that there is an extensive example of a SLA, which includes different service levels and transitions of them, and a set of interesting SLOs and role assignments. Now move on to the KPI extension of OLQ. This extension, first of all, tries to be more complete with respect to other KPI modeling approaches, and also to enable, let's say, business experts to specify KPIs in a more natural way, close to their own, let's say, language, rather than focus on using languages which are quite technical and are able to specify KPIs on a more technical level, and thus are not more suitable to this kind of users. So the KPI extension focuses on KPI and goal modeling and builds over the specification facet of OLQ again, and it can be used by the BPaaS design and allocation environment in order to specify the KPIs that will be included in the SLAs, but will also be mapped to, let's say, internal SLAs of the broker. And they are actually used by the BPaaS evaluation environment in order to evaluate and support the drill down of KPIs. And more details about how let's say, the KPIs and OLQ, let's say, language which is able to specify KPIs can be used in order to assess and drill down KPIs and support the BPaaS assessment on a forthcoming webinar on December 2017. Now, this KPI extension can be able to model KPIs as simple constraints, which are enhanced with additional thresholds in order to cover, apart from violation thresholds, also warning thresholds. It's able to specify different KPI relationships. For example, it can indicate that a high-level KPI is related to lower-level KPIs, and this can enable the KPI drill down in order to find root causes of KPI violations. We can access the metric formulas in OLQ in order to be able to draw information from external and internal information sources. So, for example, we can exploit information coming from the execution of the BPaaS, as well as information coming from external sources. For example, let's say location ontologies, which can be used in order to do some inferencing over locations, enabling us to focus, let's say, on doing some analysis of specific measurements in particular periods for a particular KPI, and do some more, let's say, for sophisticated analysis of this on this KPI. In addition, apart from being able to support the modeling of automatic measurements, also manual measurements are being supported. And in addition, KPI assessments are being expressed, and I will indicate to you what this means in the next slide. And finally, KPIs are mapped to goals, and this way can actually enable to perform a goal-based analysis in order to detect whether the high-level goals of the broker are being satisfied or not, and which is the actual satisfaction level of them. Here is again an overview of OLQ, where now we focus on the KPI extension, and the extended concepts are colored with red. So you can see here that the KPI is a kind of simple constraint which can have child KPIs. This KPI contributes to a goal, and a goal can have an end and or contributions, and there can be different types of goals like functional, non-functional, and strategic, tactical, or operational. And you can actually see that by having two new subclasses of argument, query and API call, so the query mapping on performing queries over databases, and API call on performing calls over particular APIs. So based on these two subclasses of argument, we are able to extend metric formulas and be able to specify as part of a particular application of the function of these formulas over parameters which map to the result of the queries or the API calls. And finally, there's the KPI assessment, which is a kind of measurement. So it has, of course, the timestamp and value of the measurement, but it also includes what is the current trend about the KPI evaluation, and whether this KPI evaluation maps to the violation of a warning or of a violation threshold. And of course, you can also see here that there is also the case of manual measurements which are supplied by users. So this ends actually the presentation of OLQ and the way it supports the BPaaS semantics. So, to summarize what has been presented, OLQ focuses on the non-functional aspect of services. It covers the semantics of BPaaS with respect to the specification of SLAs and KPIs. And it can be used in order to enable the monitoring, deployment, and configuration of BPaaS. And this is supported via the specification of all appropriate measurement details in OLQ. And finally, I should also indicate that OLQ enables creating interesting functional matchmaking and selection algorithms in order to support the allocation of BPaaS. And in the next telecom on April, which will be done by me, you will be able to find more details about how BPaaS allocation is being supported by smart matchmaking and selection algorithms. This ends my presentation now. Thank you very much for your attention, and I will wait for you, to make any question via the indicated way that has been showed initially in the first slides. Okay, I will wait until another minute, and then I will close the session. But in any case, this presentation will be uploaded in the website of CloudSocket, and you will also be able to see the references have been mentioned inside the presentation, and be able to study the respective business approaches that are being referred. So thank you very much for your attention. I didn't see any questions, and I hope to see you in the next webinars of CloudSocket. Thank you. Bye-bye.